Today we are going to discuss on randomized search yielding optimization. We are going to deliver certain algorithms with which the students will be able to demonstrate these various randomized search algorithms that yield optimized results. We go for various algorithms like simulated annealing, genetic algorithms, and colony optimization, which use randomization to generate results. And we first go to the first algorithm, which is simulated annealing, which is a stochastic global search optimization algorithm inspired by annealing of the metallurgy. That is, by heating and cooling, you are increasing the strength of a particular metal, which is easier to work with. The temperature is reduced slowly, starting from a randomized search at high temperature, eventually becoming purely greedy descent, and the approach is at zero temperature. A method for solving unconstrained and bound constraint optimization problems is what we are going to look at. It maintains a current assignment of the values of variables. At each step, we require to pick a variable at random, then pick a value at random, and if the assigning of the value to the variable is an improvement or does not increase the number of conflicts, the algorithm accepts the assignment and there is a new current assignment. Otherwise, it accepts an assignment with some probability depending on the temperature and how much worse it is than the current assignment. So we are always going to go for looking at a better assignment, and if the change is not accepted, the current assignment is definitely changed. The rules to be followed are very simple. They include selecting a start node, which I call as the root node, randomly selecting a child from the current node and calculating the value reflecting how good such child is like. The value of the node is always assigned to minus of the heuristic node because we want this particular energy to keep on decreasing so that we reach our particular node very fast, which is our goal node. We select the child if it is better than the current node, else we try another child. After following this, the node which is better than the current node, if the difference in the energy values are the value for the next minus value for the current, when it is positive, that is greater than 0, else if it is negative, then we try to find another child. If the child was better than the current node, then it will be selected with the probability equal to P of E of delta ET, where delta E is the value next minus value of the current node and T is the temperature. You stop doing this if no improvement can be found or after a fixed amount of time. The second type of algorithms are evolutionary based, and they are called as genetic algorithms. Here we have certain basic technologies that we have to understand. First of all, a chromosome carries hereditary characteristics. They are coded replication of characters. They are going to use optimization, and they are based on Darwin's theory of survival of the fittest and natural selection. And they are robust and complex spaces which are involved in such a particular algorithm as inputs, and they work with the coding of the parameters. They use a payoff function to find out a more fitter chromosome, and they use probability for determining all the rules. The algorithm is very specifically defined by this particular flowchart, where we will apply the various operators which we will be seeing. Now the operators perform certain operations, and the first operator is reproduction, the second is a simple crossover, the third is mutation. And here we see that we are going to do all the various operations on binary strings. Reproduction is to select the proportion of the fitness value and copy it to the next generation if it is fit, and here we are viewing a survival of the fittest. The phenotype space is then encoded into a genotype, and these genotype are then represented as genes which has a perfect length, and all these genes represented as zeros and ones contribute to our particular chromosome which has a particular length, and each individual has a particular representation, and they are called as individuals of the total population. After doing our particular processing, we could decode it finally to then represent a new phenotype space. The simple genetic algorithm thus goes by selecting the parents for the mating pool, shuffling the mating pool. For the consecutive operations, we apply crossover with a particular probability of crossover. Then we use mutation, where we flip in certain bits and we replace the whole population with the resulting offspring to be copied to the next generation. Simple genetic operators will consist of a single crossover point, by which we will then take a particular parent which is strong, and these two parents which are selected at random are then at a particular crossover point flipped between the tails and the heads which are across a particular crossover point to generate new children, as we are seeing here. So we choose at random two parents, split the parents at crossover point, create children, and this is done at the probability of crossover, which usually has a range of 0.6 to 0.9. Then we have mutation, that is, we are having good chromosomes, but we want to get better chromosome by flipping few bits, and that is called as mutation. We have a mutation rate associated, which is called as PM, and we typically have its values to be 1 upon population size or 1 upon chromosome length. Now this is all done with the help of randomness in our particular environment by having a Rowlett wheel, as we are seeing here, having different regions A, B and C, and fixing the fitness of A to be 3, fitness of B to be 1 and fitness of C to be 2, and we are then going to generate our probability values associated with this. So we assign the individual the part of the Rowlett wheel and spin a wheel in times for the end individuals. We perform a mutation whenever required to have a better output for our particular solution by having flipping of bits. We remark that genetic algorithms are instances of random processes, and mating and crossover is done with a random selection of a fit members. The next algorithm is an ant colony optimization algorithm, which is a probabilistic technique for solving computational problems. They can be reduced to finding the paths, and is a member of the ant colony optimization in the swarm intelligence method. And here we are seeing that we constitute some meta-heuristic optimizations. Ants go through the food when layering down phenomenal trails. Then we see that a shortest path is discovered via phenomenal trails. Then such ant moves are taken always at a random, and the first selection is depending upon this randomization. Then we have the phenom which is deposited on the path. The shorter path, which is more phenom trails, are seen which have positive feedback associated system to it. Then ants follow the intense phenom trails. So the rules to be followed are: this algorithm operates on almost blind sort of representation, which is incapable of achieving the complex task alone. It relies on the phenomenon of swarm intelligence for survival. It is capable of establishing the shortest route path for the colony of feeding the source and the back. It uses stigmatic communication via pheromonal trails. The rules to be followed are: follow the existing pherom trails with a high probability. What emerges is a form of automatic behavior. The more ants follow a trail, the more attractive the trail becomes for being followed. The process is thus characterized by a positive feedback loop, where the probability of the discrete path choice increases with the number of times the same path was chosen before. Thus we have certain conditions like collecting systems capable of accomplishing difficult tasks in dynamic and varied environments without the external guidance or control and with no central coordination. achieving a collection performance which would not normally be achieved by an individual acting alone. Therefore, this colony of ants will produce very good results. The constitution of a natural model, particularly situated to distribute the problem solving, is required in this particular scenario. We do require to understand what is this stigmergic. It is a particular concept associated with two individuals interacting indirectly when one of them modifies the environment and the other responds to the new environment at a later time. This is stigmergy, and the real ants use stigmergy and they go on to follow the same path, and through randomization we are achieving very good results on what the ants has given out as pheromones. Autocatalyzation is a positive feedback loop that drives the ants to explore promising aspects of the search space over less promising areas, and therefore by autocatalyzation in a positive feedback loop we go to those particular loops which are randomly generating our particular values and leading us probably to the goal that we are expecting to achieve. For our references, we have used. Thank you.